All right, so if we look at modern systems, and that could be servers, any type of software or whatever, all of these guys are very chatty. They're telling you a load of interesting and not so interesting information. And if I look at one of our routers, like a recent Cisco 8000, there's more than 1 million counters in this device. And it can go and tell you all these counters with regular cadence, like 5-10 seconds. And there might be something you might use, well, your flavor of the day or your favorite tool to go and detect change points, and then you have 1 million of those, and it spits out that particular log line that it believes it changed. And none of this is too useful, right? So you still need somebody that really understands what's going on to make sense out of this information. And what we're going to go and talk about today in the next half an hour or so is, can we ask an LLM like GPT-4 for help? So that the output is something that is human digestible in human language. And we're going to go and jointly explore how far we can go. Let's start off with something that is relatively simple: logs. So imagine you're an IT ops engineer and somebody threw you this file called klub flannel ds xdp whatever. And the guy said, well, something wrong here. Go debug. What do? Right? You open the file. There's a bunch of information in there. And then you say, well, what did Frank say? Well, we could go and diagnose. And you typically, you might open the file further. You might grab for warnings. You might grab for errors. And maybe you find something, or maybe you don't find something. Next best idea is maybe we can go and take this file directly and squeeze it into GPT-4. Bummer. I tried this, and the file, my file here, is 4,500 lines and more than 200,000 tokens. So even GPT-4 Turbo won't really help you here. And if you say, well, yeah, maybe the Anthropic people, they can go and give you Claude 2 with an even bigger context window. I can give you an even bigger file. So that might not necessarily cut it straight away. So we have to go and filter that file down. So what can we go and do in order to filter that file down? There's two main approaches to go and filtering something down, so that you have the big file, and all you want to go and do is shrink this file so that I can go and fit the remainder after filtering into a context window of an LLM. And while filtering, I shouldn't really lose the key information, right? And there's two main approaches to this whole thing. One is you can go and apply statistics, like what people do for keyword detection in documents. There's quite a few out there, and we're going to go and look at one using TF-IDF, so token frequency-based methods. You can also go and use a projection, meaning you take your file and then you come up with a projection into vector space, and then in the vector space, you're trying to go and identify clusters and saying, well, this cluster, that represents relevant information, and that cluster doesn't really represent relevant information, which is not too easy if you want to go and do this in an unsupervised way. So we're going to go and focus on the really simple thing here, which is, let's go and use a method that is well known for a couple of years to go and detect keywords in natural language documents. Term frequency, inverse document frequency. What is the intuition? If you have a particular document, and in that particular document, you see in certain tokens, i.e. words, very frequently, and on the flip side, you have a bunch of documents, and that one document is part of that, but in this bunch of documents, this word is rare. Then this is important, right? So what is frequently happening at a particular observation time, but rare in the bigger scheme of things, this might be interesting information, and we can go and use this to rank tokens or words or even lines in a document. So what we're going to go and do in our case for log files, every single line, every single log line, I'm going to go and call a document. And then all the log files in my document, I'm going to go and call the entire corpus. And what I'm now using is this rareness metric that TF-IDF gives me to sort the log file. Very, very, very simple and fast, right? So no embeddings, no vector transformations. It's just token count and token frequencies, and finally computing the cross entropy. So this is what, on the left-hand side, what it looks like, and what the sorted thing on the right-hand side looks like. This is too fine print. In order to help you, I posted all the notebooks that I'm using on Git, so you can go and follow along. And in certain cases, I'm going to go and switch back and forth between SageMaker and what we're showing here in order to go and show you a couple of examples. So the log file, let me go and highlight the top 10 lines out of there. So there's some boring shit up there, like bootstrap done. But if you scroll a little further down, and that was the original line 19 and 18, it said something like no subnet found for key flannel IPv6 subnet. So that, well, if you know flannel a little bit, you see where the problem is. But maybe you don't know flannel. Could we go and still diagnose it? By now, 10 lines, this is small, right? This sounds like we could easily fit this into a prompt for GPT-4. So let's go and do this. To GPT-4, this is the simple prompt that I used. You're an IT operations engineer. Your task is to diagnose an issue described by a set of log lines further below. And then first go and create a technical description of what the issue might be and propose a resolution. Very simple prompt, right? And this is what the thing came back with. And that's quite, I found fascinating. So yeah, well, there is an issue from Kubernetes node that is related to flannel as a CNI. OK, it knows what a CNI is. Excellent. And it reports warnings that it couldn't really find the required subnet information for the v4 and the v6 subnets. And then it says, well, in order to resolve that, make sure that you're setting these environment variables, which is what we forgot to go and do when we set this up. That's not bad, right? So this LLM thing seems to really understand logs of IT systems. That's quite surprising, to be honest, right? And if you do this with 3.5, I started playing around with this whole thing more than a year ago, and then GPT 3.5 was out. And the results were so-so. But when 4 came out, that was really a breakthrough. That was like, oh boy, this guy's understanding what happens here, seemingly, and it can help me. Now, logs are still semi-structured or semi-unstructured information. So they are looking like words. So not too big of a surprise that GPT-4 was really trained on the entire internet, that it has seen a load of Stack Overflow articles, maybe not even from here, but maybe from Japan or whatever. And it probably has seen a load of flannel failures as well. So not too big of a surprise that it knows that, but given that the corpus that GPT-4 was trained on is so large, it gives us reasonable results. So let's do the same thing with up-leveling the whole thing, streaming telemetry information from a router. So let's assume we need to go and interpret streaming telemetry information, which is typically time series data, loads and loads and loads of counters. And for that, we use the lab to go and run a couple of experiments. And that's a two-tier, simple data center style, class architecture. And what you have is on the left-hand side, on the right-hand side, there's traffic generators, Ixia traffic generators. They're pumping traffic into the fabric, loads of 100 gig E interfaces. And then we inserted artificial events, synthetic events, into this fabric and gather telemetry information from the fabric as we did these experiments. Like we shut down an interface, we filtered out BFD traffic, so bidirectional forwarding detection traffic, in order to trick the system into saying, well, there's congestion, that link went probably down, or it's not really operational as usual. And we thought, can we just use the telemetry information and nothing else to retrieve these events? Can we rediscover these events by just looking at the data without any prior training, without any kind of comparing things to a regular setup where you say, well, this is the normal thing, and then I'm going to go and train a model on the normal thing, and then I'm looking for deviations from the normal. No, nothing like that. because all of that is pretty tedious. So could we? So those are the events that we inserted. So left-hand side, you see the absolute timestamp. That's not too sexy, but the relative timestamp. We started the XCR traffic. Then we broke a BFD link, i.e. filter out BFD traffic. We shut down an interface, re-enabled BFD traffic, and so forth on a particular device. You see that listed there. So most of the experiments were done on this spine 4 and leaf 7, like spine 4, very right-hand side in the middle, spine 4 in the very, at the bottom in the very middle, and leaf 7 on the right-hand side. OK. So what telemetry information did we gather? On a Cisco device, and you have the same thing with various other vendors, including Juniper and the likes, you have model-driven telemetry. So the whole telemetry information, the counter information that I can go and gather from a device is model described. And I'm going to go and tell the router I'm interested in these particular models so that it tells me, like, OK, I'm going to go and gather that information for you and throw this over the fence using gRPC. Those are 24 individual models that we subscribe to, and that already generates quite a bit of data. And as you see, like, we subscribe to a typical raft of things that you're typically monitoring in a router, like memory information, system level information, v6, v4 information, FIP information, BGP, so routing table information, so pretty much across the board. And what we want to then do is, like I said, can we rediscover the events that we originally put in and then, well, diagnose them in a completely unsupervised way? So the first thing that we have to go and do is the data that comes in. Well, if you've done a little bit of ML anytime, anywhere in the past, you know any data is not perfectly clean. It's not perfectly timestamp aligned. There might be gaps and whatever. So we need to go and clean it a little bit. We need to go and scale it. We need to make the counters comparable. Then we want to go and detect change points. So can we go and figure out state transitions in the system that might then hopefully correlate to our events that we originally inserted, and then describe these change points so that we can go and come up with a diagnosis very similar to what we've seen from the log earlier on. Dimensionality of the problem. If you list the data, then, and that's in that notebook that I have online, then you'll see that the dimensions are 73, 34 individual columns. The first one is the timestamp, and that means I have 7,333 individual counters that I gather. Loads of information, and loads of this information, and you see some of that highlighted there. Those are packet counters from interfaces. All of that stuff is constantly on the move. And then we have 1079 individual rows. So that means we have roughly 1,000 individual observations, and they are 10 seconds apart from each other. So quite high dimensional. What do you do with this? Like if you would go and plot it, it would look like this. Very useful, right? No, it's not. So we need to go and transform the data a little bit so that it's a little bit more friendly to processing. And what we typically do, and I think here this is good enough. So we timestamp align the overall thing. That's important, so that everybody is just on like 10-second intervals. And then we scale the data and normalize the data so that every single counter is not like trillion or whatever, but it's sitting between 1 and 0. We also smooth the data a little bit to make sure that like observation problems that you have in a system where the system was just not fast enough to gather the data, that these things are not really confusing you later on. And in loads of cases, we use the differential between individual timestamps because you're interested in the change. You're not necessarily interested in the absolute value. And if you do this, well, lines that were just like monotonously increasing, like on the left-hand side, suddenly turn into something that is pretty meaningful, where you see indeed change in the system, where certain things happen and then they don't happen. And we can go and read stuff into this. So resulting data, clean data for our leaf 7 is this. It's still high dimensional. It's still 7,000 dimensions. And it's still like roughly 1,000 individual observation, so timestamps. Now, a while ago, a couple of researchers, including Jan Rexford from Princeton, they looked at the nature of network data. And they found something quite interesting when they looked at the main variants of data, i.e. they looked at PCA, so principal component analysis, and they were trying to understand how many dimensions have already most of the variants covered. And that's the plot on the right-hand side. And they did this for Abbey Lane and a couple of really large networks like Giant. And what they found is very interesting. You find here, for instance, if you look at Abbey Lane on the the blue line on the very top, that something like 10 principal components, so 10 vectors, are already capturing 95% of the variance, i.e. energy, descriptive energy in the system. So the problem that looks like very high dimensional with 7,000 dimensions in reality is not that big. So there is a load of redundancy entropy in this system, and we can go and filter that out. And for humans, PCA is not a perfect projection in order to go and do dimension reductions. So there's better methods that are more visual. One particular method that has worked really well for us is T-distributed stochastic neighbor embedding, or easier, T-SNE. What does T-SNE do? It takes, or it tries to go and project from high dimensional space, like 7,000 dimensions, into 2D or 3D. And while doing the projection, it tries to keep the structure of the data. It's not that things that are, the overall dimensionality or the dimensions or the Euclidean distance between 2 points, that doesn't really tell you too much. But if things are close in high dimensional space, they will be close in the map. And if things are far away in high dimensional space, they will be far away in the map. So it keeps the structure of the data, and that's exactly what we want. And if we do a plot, and I think this is easier if I show you that in a notebook. So if we do a plot of this whole thing, and I might even want to go and animate that thing. So every single dot here is a projection of the high dimensional space into 2D. And you see that the system, and this dot is just like now jumping timestamp to timestamp to timestamp to timestamp. And you see that the system is relatively stable for quite a while, and then it jumps to another state. And then it's, again, very stable for a while, and then it jumps to another state. And something that you don't really see too well here is these little red dots. These little red dots are the times when we did something, when we inserted our synthetic events. So what you see here is that these transitions from one cluster to another cluster almost perfectly correlate to us inserting a synthetic event, like break in a BFD session. So this tells me structure, and if I have the structure, then I can go and also do this and redetect that structure with something like dbScan. So I can go and detect these clusters in the map, and then say, well, those are my change points here, where I'm having one cluster, the next cluster, and I kind of highlighted the transitions between clusters with these big gray bars. So I can capture these change points. So I understand now that something happened between this cluster and that cluster, but I still don't know what the something is. Can I go and describe this? Because the problem is still there, that I have a bunch of counters, and now tell me, what is the problem? I know that there is a state transition in the system, so that's already great. But how do I go and switch this to, I understand what the state transition is all about? So let's go back to this one. So I think I highlighted that to you using my finger. And dbScan, just for reference, it's something that is also pretty well known in the community by now. It's roughly 10 years old from a reasonable clustering mechanism. So one thing that you might say is like, oh yeah, let's look at the changed features. and maybe there is descriptive enough. So maybe you can go and look at a particular point in time and then say, well, let's look at all the features that change, and maybe there are not too many, so that we can use these individual counters to go and describe the change. Not really. I did a plot, and the orange line up there is 7,333, so 7333. So that's the total number of features, and out here I plotted the number of features that change from timestamp to timestamp. And that's roughly 5,000. Not too good. So 5,000 things that change all the time, not really helpful. So if I zoom in at a particular point in time, so the 4,800 point timestamp, this is this one here. So this is this transition from here to there, from the very top to the very bottom down here. So at that particular point in time, if you zoom into this, the differential between timestamps, then yeah, there's not even a pattern, right? You can't really say that there is something really specific where I say, well, this helps me now diagnose. So too many timestamps to go and really make sense out of this. So again, we have to go and reduce the problem. And when we did this, and this is mostly work that one of my colleagues, Thomas Felton, has done. He wrote a PhD on this, and we published a couple of papers on that even. So we look at two things. One is, how does a counter change? Is it a spike? Spikes are not too meaningful, by the way. Is it a step function? Step functions are really meaningful, very cool. Or is it like a variance change or a frequency change? Those are meaningful as well, so they can go and tell me something. And then he had a pretty clever idea. So because the change metric in itself, there is still a load of things that jump. He had a pretty clever idea. And that pretty clever idea he loaned from what we've seen earlier on from logs. He said, well, these sensor paths, these descriptions of the counter, they're pretty long and wordy. Can't we just use these descriptions and use these descriptions to rank the importance of a feature? And the answer is yes, we can. It's quite fascinating. So a long sensor path, we tokenize into smaller chunks, and then we do exactly what we've done before. We look at all the Yang models, and if something is rare across all the Yang models, but very, very frequently seen at a particular point in time, it is more important than stuff that is very frequently seen across the entire corpus. So exactly the same logic that we used for TF-IDF on logs and, well, keyword extraction, we use here as well. And this freaking works. So we did something on this particular event. I highlighted this where the system transitions from the very top to the very bottom. You saw that change. And on the right-hand side, you see what is being spit out as the top 5 features. This is all related to BFD. That's the first thing, and then it's relating to the interface, 100 gig E and whatever. And now, can we do the same thing that we've done before and ask an LLM about this thing? Can you go and describe this change to me? Of course, we can try, right? I tried this first with GPT 3.5, and GPT 3.5 had no idea of what Yang is. I gave it pointers to RFCs and whatever. It didn't really help. Yeah, and for those of you that are in open daylight, hard to believe, right? So that's something that is that old GPT 3.5 wasn't really trained on. But 4 is different. 4 has seen every single RFC. 4 knows what Yang is. So here is the prompt. You're a networking expert. You're diagnosing a network issue based on telemetry information received from a Cisco iOS router. Below is a list of sensor paths. And what I've given this thing as well is not only the sensor path, the name, but also the amplitude of change. I need to be a little bit helping, right? So amplitude of change and the name. And then saying, well, this is an extract of those features that are the most important. And again, the answer asked is, go and describe the thing, tell me what the issue is, and come up with a resolution. Description, yeah, the telemetry data from the router indicates an issue with bidirectional forwarding detection on a particular interface, like 100 gig E16. And then it does what the GPT parrot does, right? It tells me what BFD is. Okay, fine. Let's get forward. But it sees that there is a bunch of session up and down counts indicating that the session went up and down and it didn't really come back up. So something's going on there. And the resolution is also pretty interesting, because that's exactly what you would do. Check the physical layer, check the BFD configuration on whether BFD is meaningfully configured or not. So this thing really blew me, I have to say, because we started with nothing. We didn't really train a model to go and compare a good network to a network with issues. No, all we did is we looked at counters, we tried to go and detect change points in the counters, and then we selected a set of these counters and fed that into GPT, and the thing told me, well, this is a problem with a BFD session, and if we go back to this particular point in time, you might remember this particular slide that I've shown you, right? The thing that we're diagnosing is indeed where I broke a BFD session. So, what does that mean? Our dear parrot, GPT-4, don't do this with 3.5. Try it with 4 or not, even better, Turbo. The thing knows IT and networking, and it can even interpret different types of telemetry information, including network telemetry information that are a little fuzzy, right? So if you feed this to a junior, I think GPT is doing better than a junior networking engineer. Nah, this is mind-blowing. Anyway, so to wrap up, I think we can ask this thing for help. We can ask this thing for help to diagnose issues that we have trouble with diagnosing today. So there is a raft of issues, and all of us, the networking industry, has built a large set of quote-unquote expert systems that say, well, this is the input, this is the setup, and then you're basically going through a decision tree to go and tell you, do this. Go and fix the DHCP server. This is brilliant. It's deterministic. The outcome is useful. But what if you are debugging a problem that you've not seen before, where you don't really have an ontology, where you don't really have an expert system knowing what the setup is? Or even worse, you have a scenario where you receive a bundle, a tarball with loads of logs from different systems. And then your expert system is just like focused on vendor 1 or vendor 2, but not vendor 1 and 2. So if we start with the data instead of like fitting data to a problem and then have a decision system on top, we can start with the data, as you've seen, and we can read into that data and ask GPT to interpret that data for us. And eventually, it moves us closer to what the quote-unquote root cause is. I'm not holding my breath, this is correct always and all the time. But guess what, right? Either it saves you time, or you're on your own anyway. Right? So if it saves me time in 50% of the cases, I talked to one of our technical assistance center guys, and he said, well, Frank, this is kind of cool, because if you're right, even in 50% of the cases, I would try it. Because in 50% of the cases, it saves me time. Otherwise, like, yeah, well, I start over. So I think, yeah, go try it. Thank you so much. Any quick questions? I think we have probably time for one or two. Oh, yeah, it's always the guy at the very end.
So the heavy lifting of your work is not necessarily passing the data to GPT-4. The heavy lifting is the data engineering part.
As usual.
But for that, you have to have a full experience of years to where to look and then experience of what tools you should use to filter that data and look in what variables and parameters. Have you figured out to automate this data engineering part from network observability perspective? Because if we can, this is the 101 network engineering. If there's something flickering in the network, first thing you should do, change the goddamn cable. We teach that as the very first thing to a junior network engineer.
Yeah, no.
So this is pointing your 50% fixing the problem, change the cable or changing the switchboard. Okay, let's reverse back.
You're absolutely right. So cleaning the data that's your mic, not mine. I have one. Cleaning the data and doing the ELT part, right? Extract, load, transform. That heavy lifting, you still have to go and do, as you saw, right? So I need to go and shrink the thing to something that is small enough so that GPT can actually do something meaningful with it. That's the hard part. And then, well, I just sit there and hope, right, and pray. There is a load of observability systems that do ELT pretty well, especially when it comes to logs. Streaming telemetry, not so much. But for logs, you have all these alerts. But wouldn't it be nice if, and I hope that all these observability company vendors, I work for one, they're all busy bolting on AI capability so that the whole thing becomes more human digestible. Because you can indeed ask an LLM to not only interpret the data, but also aggregate the data. So summarize the data and to come up with something. I think this is like, I only had 30 minutes, right? So you can go far further with this. This is the starting point. You also don't want to go and do this for one file. You want to do this for many files. You want to go and do this for all your alerts that you see, like this dashboard where everything is red. Where do you look first, right? So I think that we can go and move observability to a completely new level if we do this. And we might even be able to go and help these classic systems to not ask what all these guys do, like go and transform your data on input to my schema, whether it's open telemetry, SIM, or what have you. Maybe you can again have generative AI transform the data for me so that I start with the data and I don't really have to go and come up with regex that maps certain fields to my schema, which is another painful thing. But yeah, well, I think we're at the start of a journey here. But your points are all very valid.
So maybe one follow-up, as Cisco has acquired Isovalent, which is known for eBPF technology. So one of the basic assumptions in your presentation was that there's a action-reaction paradigm, right? So there's something happened that caused some output to be generated. What if there's an action, but there's no reaction you haven't seen because you don't have the proper data? So coming back to generating the missing data as a gap analysis, using eBPF, have you ever considered going that path to enrich your data sources?
It's a good idea. So I think if you're not seeing anything, can I go and ask the system for more? Because we did 7,000, right? So I can
but
also
those 7,000 has been there for 10 years, and nothing new counter added to more prescriptive resolution.
Yep. We have on routers, we have a feature that we built back in 2019, which is called AI-driven telemetry, where the system learns based on your config what you want to go and spit out.
That's awesome.
So that, and it does the pre-filtering on the box. So very similar to what we've done here with semantic feature extraction, so that you're not throwing all the data, but the data that the router believes is relevant for you. All of these are heuristics, right? So we have to be a little careful that we're not claiming like we're 100% correct. But if we're okay with meaningful level of accuracy, like 60, 70%, then I think we can go and do a lot of good things here. Because I talked to a carrier earlier the week, and they said, well, we really trimmed down all the telemetry exports from all our devices because we don't know where to go and put all the data. Yeah, good if you're a data lake company that sells data lakes, right? But not good as a customer. Anyway, thank you so much, and enjoy lunch.